Hi everyone, I hope your break is going well. And so, before I get into the topic of this particular discussion, I want to put everything into perspective. And so, up until this point, what we've been doing was essentially building up our toolkit. And so, we've been, the language of choice here is C++, and we're using this concept of object oriented programming tied in with these notions of polymorphism, in particular as it pertains to generic programming, which is implemented by using templates through C++. And the idea is to incorporate all these things to build up our data structures, incorporate our algorithms, and of course wrap that all within a simple interface for us or other people to use to solve the problems that they want to solve. And so the motivation, I think you can appreciate, right? If these are the tools we'll be using, and we have to make sure we have some fundamental understanding of them. The analogy would be, a carpenter who doesn't know the differences between various hammers will not be as productive as one who does. And so now that we have a understanding, or at least a certain level of comfort with these tools, we can go ahead and move on to actually using them to develop these things, these data structures, and these algorithms. And so this approach is, you can think of it as a bottom-up approach, right? So we're starting with the fundamentals and building ourselves up to the point where we can get to the top with the complete abstract data type that we'll be developing. Another approach to take is to take a top-down approach. That is to say, examine solutions that exist, and the idea is that this will provide us some insight as to how we can improve upon or design our own solutions doing roughly the same thing. And so what I'm referring to here is examining the standard template library. And so 30 years ago or so, many of the authors of the C++ standard, they took a data structures course, and they recognized that there are many common elements within the solutions people were implementing for the problems that they wanted to solve. And so they thought to themselves, well, maybe since these elements are so ubiquitous within programming, it would probably be a good idea to develop some solutions so that people can just pull from these solutions instead of spending the time writing their own. If they don't, so the idea is to not reinvent the wheel. And so that's essentially what the standard template library is that they got together, they use object-oriented programming, they use this notion of templates, and they developed a set of what we call container classes, essentially these abstract data types that are designed to hold information. And they also incorporated a bunch of algorithms to allow people to operate on these container classes. And in a sense, this is where we're going with this course. We're getting ourselves to the point where we ourselves can design the standard template library. And so, you might at this point ask yourself, well, if there's solutions that already exist, what is the point of actually going through this process of learning about them? Well, for one, it ties back to this idea of the carpenter and knowing its hammer. In order to make effective decisions, efficient decisions on which of these tools to use, you kind of have to understand how they work. And in addition to that, it might be that those solutions might not work for what you want. And so in those situations, you have to have the ability to develop custom solutions. And so now with this being said, when you leave this class, it's a good idea for the things that you're implementing. If it's being done in C++, you should first begin looking at existing libraries like STL, and there's many others, one of which is called Boost. But yeah, so start looking there for your solutions in terms of your data structures and algorithms. But in situations in which those particular solutions don't fit your needs, then you have to look elsewhere and or develop your own. And so in order to even begin that process, you have to have some underlying understanding about how these things are done, which is the purpose of data structure courses in general. Well, regardless, let's go ahead and dive into it. And so let's take a look at some code. Here, I'm including the IO stream because I'm going to be sending things to the output or the console. I'm going to be using the string. And then here's two includes that you may not have seen before. one is for a thing called a stack, another is for a thing called a queue, and I'm just indicating that I'm using these particular objects from those libraries. And so within main, we see I'm declaring a stack, and here we're using templates, right? So this is a templated container class that stores integers. So this stack object stores integers. Its identifier is is. And so we should understand at this point that this is invoking the default constructor for a stack, and it turns out that a reasonable implementation for a default constructor for a stack is essentially creating a stack that has nothing in it. And so even without talking about what this is in detail, you should have some understanding of what a stack is. In particular, you use the statement, I have a stack of books, or I have a stack of plates, and there's this implication with regards to how you interact with a stack of books and or a stack of plates. In particular, when I put a book on top of another book, the first book that I will remove from this stack is the last book I put onto the stack. All right, so it's kind of difficult to imagine by saying it, but you can envision this, right? And so actually, let's go through this process here. And so I call the stack, and I push onto the stack the number 5. And so let me go ahead and just create my stack. So here's my stack. It begins being empty, so there's nothing here. And so when I go ahead and put the integer 5 onto my stack, I should see something that looks like this. So boom. There's the integer 5 on my stack. And right now, there's only one thing on my stack, but I can say that this is the top of my stack, right? That kind of makes sense. Now, when I go to put the integer 7 onto my stack, how do you imagine this looking, right? And so just think about a stack of books. One book, if I put another book onto my stack, it's probably going to be on top of the last thing I placed onto the stack, all right? And so we can imagine the stack now looking like this, and of course this is now the top of my stack. And again, we can push the integer 8 onto my stack, and I can go ahead and put the 8 onto my stack, and now this is the top of my stack. And so when I go to examine what's at the top of my stack, what do you expect to have printed with the cout statement? Well, if you examine the picture, or if you just use our intuition, we should just examine, well, the top. And in this case, 8 is the top of my stack. It's the last thing we put onto the stack. And so we're going to talk about this in detail later on. Here I'm just introducing this. But, the term is, or the behavior of a stack is that the first item that is placed onto the stack, so first in, is the last item out. Or in particular for this, the 5 was the first item on my stack, and so if I wanted to get to this 5, I would need to first remove the 8, then the 7, and then get to the 5. So first in, last out, philo. Or if you'd rather, last in, first out, LIFO. These are the same thing. They imply the same behavior. Now, and so let me go ahead and run this so you can actually see this occur. Let me get rid of this because we'll talk about that next. And so let me execute this code. And what we see is, so here, the first cout statement should indicate 8. And then what I do here is I pop the stack, which is essentially just removing the last item. And so we should see 8 happen here, or 8 being sent to the console. We pop the stack, which essentially for this picture, we essentially remove this item. This becomes the new top. And so when we see out the top again, we should see 7. Boom. And so let's see. And so we do indeed see that. So 8 and 7. And so this notion of a stack just implies its behavior. And given its behavior, this is how you would, presumably interact with it. And we'll talk about the various situations in which we could use these things to solve problems. And so on the other spectrum of behavior, we have what's called the queue. All right, and so here I declare a queue. In this case, it's gonna contain strings. The name of the queue is SQ, and so Now with the stack, remember, so the stack was kind of like this idea of putting things on top of each other, and then we just access the last item that we put onto the stack itself. And so when you think queue or see the word queue, you should immediately think of lines, right? So lines at the grocery store, lines within the bank. And so when you get in line, you wait until it's your turn, and then whoever, the teller or the register person, will get to your order, and then you could leave. And so that's exactly the behavior of this queue within the STL. And so let me go ahead and create my queue. Here's SQ. SQ. And so this idea of pushing Malcolm into the queue or putting in line, this is just Malcolm getting in line. And so right now there's no one in line. And so let's just have Malcolm get in line. There he is. And now let's go ahead and indicate that this is now the front of the line. And so when River goes to enter the queue, she would go in after Malcolm, right? And so we can imagine, let's imagine this is the front, and then so the queue, people enter from the queue from the back this way. And so let's go ahead and place River within the queue. Boom. And then now we see Anara come into the store. She picks up some candy bars and goes ahead and enter the queue to pay for it. Boom. So she enters the rear of the queue. And so if we want to examine who's currently in the front of the queue, we just say, well, here's the queue, here's the front of it. We should see this send to the console the fact that Malcolm is currently in the front of the queue. And so once Malcolm is done with his transaction, we can pop the queue. And so this idea of popping the queue means we remove the front item from the queue itself. And so we pop the queue, and then Malcolm should go ahead and be on his merry. All right, so he goes home, and River becomes the next front of the queue after Malcolm's popped. And so this first cout statement should indicate that Malcolm was in the front of the queue, and then this cout statement, after we pop Malcolm, we should see River at the front of the queue, and it'll be her turn to do whatever she needs to do. And so let me go ahead and evaluate the code thus far. And so, yep, we do indeed see that Malcolm was the front. We popped him, and then River became the front of the queue. And again, I'm just introducing these things. We're going to talk about them in detail next week. But so here's the stack and queue. They end up being extremely useful for many applications, but we will see them again. Okay, and so there's another extremely powerful STL object. In particular, you might have seen it already, although you have encountered something that behaves just like it, and as you'll see in a second. And so another object within the STL is called a vector. And so it's inside the vector library. Again, all these are part of the standard library. And so here we see I create a vector of strings, right? So now this vector contains strings. Its name is strs. I have a vector of integers. Its name is nums. I declare a vector of robots. The name of this vector is robots. And then a vector again of int. And then let's examine what all this is doing. All right, and so these three, yes, they're declared to create different things. Again, templated, so that this one's string int robot. But we see that when we declare a vector in this way, that is to say, we're invoking the default constructor for a vector, it's reasonable to think that this vector currently has no elements, right? That seems like a reasonable default state for a vector in which we have in which we invoke the default constructor, which is in fact what happens, right? And so when I declare strs, let me slide this down, we essentially create the vector strs. It currently has no elements, right? So this is blank right now. Let me just indicate that by just that. There's strs, here's nums, all right? Again, the default constructor is currently empty. Here's robots, currently empty. And now when we get down here, what do you think this is doing? So this is a parameterized, or this is invoking a parameterized constructor for a vector of ints. And so it turns out that this essentially pre-allocates enough space to store 3 ints, right? And so let me go ahead and create geeks. And so the 3 indicates that we want space for 3 ints. And it turns out that the way this is implemented, without any other information, these memory locations for this vector is initialized as 0. So this is what this would look like after this creation of this construction of a geek vector with with enough space for 3 integers within it. Okay, so that's great. And so now what? Well, let's go ahead and use some of our vectors. In particular, let's go back to our str vector, or our vector of strings, and let's push back long. And so we go to this. When we push back long, essentially, well, there's nothing in the vector, and so essentially we're just putting an element in the vector itself. And so let's put long within the vector. And so if this is the front of the vector, this pushing back of Molly will put Molly after long. Right, and so let me go ahead and do that. Let me do it this way. So this is the front. This will be the back. So let me go ahead and put Molly into the back of the vector. And so now, given this, I can go ahead and go down here, go back to our geeks vector, which has these elements within it. Right, and so when I try to push back the number 1, 2, 3 into the back of my geeks vector, or my vector of integers, where does it go? And so if you think carefully of how it behaved up here, right, it added, each time I pushed back, it added a new element to what was currently in the vector itself. And so pushing long pushed him into an empty string, pushing Molly pushed her behind long. And so it seems like it created space for these particular elements and then placed them in there. And so pushing back this 1, 2, 3 into geeks, which already has space for 3 elements, would put 1, 2, 3 at the end or in the back of the vector itself. Okay, and so that's one thing you have to keep in mind with these vectors, that push back will actually create a new element in terms of what already exists and then place the element there. And so one advantage, or one convenient feature of vectors, is that we're allowed to use the indexing operator that you saw with arrays, and of course pointers pointing to arrays. And so doing this should operate the way you expect, the same way had geeks been an array. And so this means go to the 0th element and put the value 42 there. So essentially, after executing this line of code, we should see 42 there. Let me go ahead and scroll this up. And then when I see out geek sub 3, this is the same thing as if it were an array. We go to the 3rd element, or the index 3, which is the 4th element. And so we should see out 1, 2, 3 after this line of code here, right? And so 1, 2, 3. And now you have to be a bit careful, right? Remember with arrays, when you try to index past the bounds of the array, that leads to undefined behavior. This is the exact same situation here with vectors, right? And so if I try to access this index 4, 1 element past the last known element of geeks, this is considered undefined behavior and can lead to many, many issues. And you would hope that your program would crash in this case. In many situations it does. And so now, that's one thing that you have to be careful with. And so even after all this, you should have an inclination in terms of how these vectors are implemented. And so if you didn't realize it, it's essentially a dynamic array, which allows us to do all these things with that. That's the same as if it were an array itself. Although there's a bunch of different things on top of that that make vectors much more convenient and unique to that of arrays. But if you understand that underneath all of this there is an array somewhere, this gives you a lot of insight in terms of how you can use it in the various situations in which this particular solution is more effective over others. But again, we'll get into all of this in detail later on. Okay, and so excuse me, we know that this is bad, so let me get rid of it. Now if you want to quickly obtain the last item within a vector, you can do it through this call back. Right, and so this should be intuitive. I'm just getting the last element that's currently within my array. And so doing this should return also 1, 2, 3. Now, to remove the last item within this vector, I just call the pop back, right? And so pop back once would essentially get rid of this element, and then pop back again, we'll get rid of this element. And so one thing you have to be careful with this pop back, it actually changes the size of the vector itself, right? And so this is something that's a bit different from arrays, because we know that compile time arrays or even dynamic arrays, unless you do something in terms of reallocating, their size is fixed, right? And so the behavior of these vectors is that their size is not fixed, and that's one of the advantages over arrays themselves. Although it's the interface that we're dealing with here, and how it handles it is up to whoever implemented this particular aspect of the library. But you have to think of it as if these elements were actually removed from the vector itself. And let me go ahead and do that. Boom. Let me bring this back. And so after these two pop backs, I remove the 1, 2, 3, and then the 0. And then so again, so the cautionary tale here is that if you're popping things, you have to just remember how many elements you have. And so doing this after these two pop back calls would crash the program, right? Because there is no index 3, no third element, no fourth element in particular in this vector. Sorry, this would have been fifth element. And so you can't do this. Be careful. This would crash it. Okay, and so a bit more in terms of vectors. I can also declare a vector like this, where, so this is a vector that contains integers, its name is vals, and so let me go ahead and create vals. And so this looks like I'm pre-allocating enough space for 2 elements, so let me go ahead and bring those in here. But it seems like, let me get rid of this and this 444 should be, or it's reasonable to believe that this is probably the initial values for these elements I pre-allocated. And in fact, that's the case, right? And so this becomes 444, this becomes 444. And so this is one way to declare a vector with some pre-allocated amount of memory and then initialize each element within the vector with some starting value. And so given vals being created thus, I can push back 999. Again, that creates a new memory location, which will place 999 within the vector itself. And so one convenient feature of these standard template library data structures is that you can get the size or information with regards to the size of the object. And again, so with arrays, you don't have this. And so you can do this, well, although with the newer standard, they have an actual array object, but we're not going to incorporate those just yet because I think it was just going to confuse you with regular arrays. But regardless, so compile time, the traditional compile time arrays do not have size. You have to keep track of that on your own with another integer variable. But with vectors, you can get the size of the vector by just calling this member function size. And so this should return, in this case, a size of 3, right? Because I currently have 3 elements within vals itself. And you can also have, each container class has a Boolean function called empty, and this will return true or false depending on whether or not your data structure is empty, right? So if this vector is empty, this will return true, and then we should expect that this would print under that case. Although in this case, it's not empty, and so we're not going to see this. So anyways, so let's move on to other container classes. Or actually, we're going to, so let's talk about this next fella. Let me set this as startup. And so this next container class, it's called a list, right? And so it's within the list library, surprise, surprise. And then it's all these are part of the standard library. And so I can declare a list like this. So list, it contains floats, its name is LF. And so it looks like here I'm doing a few operations. I'm pushing back, and then I'm pushing front. And so what does this look like? And so again, we're going to talk about this in extreme detail later on, but for now, when I declare a list, again, this is calling the default constructor, and a reasonable default state for any container is that it's empty, right? So when you go to the store, pick up some Tupperware, it would be a bit disconcerting if that Tupperware had some cookies in it at the point of purchase, right? And so these containers begin empty, and so here is say LF. It starts out as being empty, and I'm just going to represent it like this. So it's an empty container that stores nothing right now. So this idea of pushing back the float 1.1, we can imagine it looking like this, right? And so now for a list, let's say here's my 1.1. It's in my list now, and so let me go ahead and represent that with this particular representation. And again, we'll talk about this in detail next week. Although you should probably give us away a lot with regards to how it's implemented, but again, you don't have to understand any of this now. I'm just sort of introducing the concepts. And so now this sort of, we see this chain of events where we have an element within LF, its particular value is 1.1, and so now we consider this to have one. This list has one element within it, in particular to float 1.1. And so after this, when we push back 2.2, we can imagine it looking like this. So here's our 2.2, and so the way we understand that this is the back of the list is through this relationship. All right, so we can have it look like this. And so now it's our understanding that the first element is this item, and the last element and second element is this item. Now, when we go to push this 3.3 to the front of the list, I'm sure you can imagine it. All right, so here's the 3.3. I can throw it in here. And so if the intent is to have this the front of the list, that just means that we just have this refer to that in this way. And conceptually, you should understand that the following relationship should be like this, right? And so given this, we should understand that this is the first, this is now the second because of this item being pushed to the front of the list, and then this is the last because of the order in which we executed these lines of code. And so that's that. And so when we want to actually read these memory locations, it turns out that lists cannot or do not have this indexing operator associated with them. So I can't read it like this, right? And so this is illegal. Lists do not overload the index operator so that you can do this. And we'll understand why actually after we discuss list. And so we need a way to, access these items within our container. And so to do that, we have to introduce this idea of iterators. And so let me bring this back to discussing vectors, because that's something we understand. We know that we can create a vector like this, and we can add elements within it. We can push back, and we can iterate through this particular vector by using the indexing operator. That should be clear because underneath it, it's a dynamic array. But given this, turns out there's another way to actually iterate through the vectors and all container classes that we see within the STL. And so let me go ahead and illustrate this by using this example. And so here I declare a vector myVec. And so let me go ahead and create it. Again, this invokes the default constructor for a vector, which means it has no elements within it. And so when I push back 1, 2, 3, 4, then push back 5 and 7, we can imagine that the vector would look like this, right? So this is the state of my vector. This is the first element. This is the last element. And so another way, instead of using the indexing operator, we can create an iterator. And to do that, you simply say, myVec is a vector of integers. And so I need to create an iterator for a vector of integers, right? And so this indicates to the compiler that whatever I'm doing, it's something with regards to a vector of integers, the scope resolution operator, and then following that is the keyword iterator, or rather it's an object of this type. So it's an iterator for vectors of iterators, or vectors of integers, sorry. The name of this particular object is IT. And so given now that I have an iterator that can iterate through vectors of integers, I can have IT start at the beginning of my vector. And so let me go ahead and create this iterator. I'll do it here. Let me move this down a bit. Here is my iterator IT. Oops. IT, dyslexia. And so currently, after this particular line of code, it's not pointing to anything. So quote unquote pointing to anything. I'll expand upon that in a second. And so after I execute this line of code, this is now, the IT is pointing to the beginning or the first element within a vector. And so we can imagine after the line of code is executed that this is what we see. All right, and so this iterator now points to the first element of the vector. And what I can do here is I can use this star operator to have IT provide to me the value at the thing it's pointing to. And this should look very familiar. In fact, this is how we operated with pointers. And it turns out that the developers of these classes made it such that these objects behave in that way. And so I can treat this IT as if it were a pointer to the beginning of this vector itself. It technically is not a pointer, but you can treat it as if it were. And so when I increment IT plus, this essentially means that I want IT to point to the next element. So let me represent it this way. And so when I execute this statement, we should see 5, right? Because we're printing what IT is currently pointing to. Right, so let me go ahead and insert that. So the first cout statement should print out 1, 2, 3, 4. The second cout statement should print out the value 5. Alternatively, we could also start at the back of the vector, right? I can have IT point to the end of the vector itself. Now you have to be a little bit careful here. The way these classes are implemented, the end is actually the element one past the last element of the date of the container itself. And so this IT, let me move this around a bit. This having IT point to the end of the vector actually looks like this. So it's not pointing to the 7 as what you might expect like this. So this is not what this is doing. It's actually pointing one past. So this is actually where this iterator is currently pointing to. And then there's a bunch of different reasons as to why this is the case. It's just to make things more general. And we'll see plenty of examples later on as to why this makes sense as opposed to having it here. But so this is the end of the vector. So one element past the actual last element. And so if I wanted to actually print the 7, I need to decrement IT by 1. Right? And so IT minus minus moves it back one element, in which case at this point the cout statement will send 7 to the console. If I do it again, excuse me, this will move this down to the 5 like this, and so this statement should print 5. And so using this iterator object for vectors of integers, I can loop through each item, right? And so here I can start out my iterator by pointing to the beginning of the vector. While my iterator is not the end of my vector, I can grab the value within that memory location, quote unquote, and then increment it to get the next few. And so we should see that this will print out 1, 2, 3, 4, 5, and then 7. And so the reason that this says that the end is implemented to, well, the way this is implemented is so that the end is the last element, is for these loops like this. If for whatever reason they implemented so that the end was actually the last element, the logic for the for loops would have needed to change to include this last element. And so, it's a minor point. I don't really want to dwell on it. But doing it this way means that for the last iteration of this loop, we just go here, and at this point we just stop. But so without having it stop, without having the end being here, we would need to change the logic. Otherwise, this 7 would have been omitted from this loop. But anyways, I don't want to dwell on it. It's just it's a way to generalize your code, or to ensure that the loops that you write are similar to that of as if you were dealing with arrays and other data structures. Anyways, that's how you iterate through vectors. And so how do we use this to iterate through the list? Because remember, with the vector, it's easy. I could just use the indexing operator. With the list object, it's not quite the same situation. And so let's go ahead and change it so that instead of having a vector, we have a list, right? So let's go back to our list example. Well, actually, let me execute this so I can convince you that these do indeed print out the things that they do. And so let me go ahead and this should print out 1, 2, 3, 4, then 5 and 7. And so we should see 1, 2, 3, 4, 5, 7, 5, and then 1, 2, 3, 4, 5, 7. Of course, end lines between. So let me go ahead and save all this and evaluate. So, so I have some. Oh yeah, so I printed the proof vector using the indexing operator. So proof has 571, 571. Then we get down to here. We see the 1, 2, 3, 4. Then the 5. Let me move this out to the side a bit. And then the 7, the 5, and then 1, 2, 3, 4, 5, and 7. Okay, so the behavior is what we expect. Okay, so going back to the list, if I want to actually iterate through my list, it's the same thing, right? And so here I have a list of floats, and so that means I need an iterator for a list of floats, right? And so list of floats, or float, sorry, and then the iterator for this particular type of container, IT, doesn't matter, it's just an identifier. And so I can have IT, well, I can do it here as well. So it equals, I can initialize it so that it begins at the beginning of LF. And with this, I can, well, I can use a loop, right? So for IT, well, I did it here. So let me go ahead and throw it into my, it's gonna make your loop ugly. You can do this. This is sort of akin to having int I equals 0, essentially. So this iterator beginning at the beginning, and then while my iterator is not the end of my list, and then I can increment, and then from here I simply just print out what's currently in LF, right? And so let me go ahead and set this as startup. Go back to my list, and so we should see so I'm starting at the beginning, so we should see it print out 3.3, then 1.1, then 2.2. So let's go ahead and run this. Yep, 3.3, 1.1, 2.2. Okay, and so that's how you use an iterator for vectors and list. Let's go ahead and talk about the intricacies behind actually having these containers store things a bit more complicated than the scalar primitive or the primitive data types that we've been talking or seeing so far. And so let me go ahead and go to this line of code here. And so here, I declare or define a robot class. And so right now, within the robot, all I have are some member variables. All right, so it doesn't matter. Just so I have a first member variable who's of type string, second of type int, third of type float, and fourth of type integer pointer. Okay. So that's what it is. So when I go to main, I can create a list of robots, and this should behave the way you would expect in terms of just even a list of integers and a list of strings. This is just going to be the same thing, but with robots. And so I can, well, first I'll declare a robot, and this robot is just a regular robot I haven't done anything with yet. And so I initialize some of its member variables. This is public, so I can do this, although conceptually this violates encapsulation, but again, we're just doing this to illustrate a particular point. And so I initialize first to I love C++, second to the number 300, third to the float 3.14159, and fourth I dynamically allocate a new integer, and it has the value 42 within it. And so what does this particular robot look like? Excuse me. And so let me go ahead and create some space. So after this declaration and subsequent initialization or assignments to the member variables, we should see something that looks like this. All right, and so the member variables, there's the robot R, here's what it looks like. Boom. Okay, and so here I'm going to go ahead and put this robot into my list. So I'm going to push it into the back of my list. And let me go ahead and create my list. I'm just going to do something like, let me just wrap this in within. So, well, let me go ahead and create, here's my list. It starts out empty. I'm just creating space so I can throw stuff into it. And so, boom. This is the list of robots. Currently, after this, there's nothing, or after the declaration, there's nothing in it because I don't indicate that there is anything within it. And so when I push back R, essentially within this list, I should have something that looks like it in here, right? And so we'll talk about what it actually does later on. And so given that I have a list of robots with one robot currently within it, I can use an iterator to have it begin at the beginning, and then I can refer to its member variables the way we normally would had I had a pointer to various robots, right? And so IT points to the first robot within this list. I can dereference this to get the first member variable, and again, I can hear the arrow operator does the exact same thing, right? So with pointers, it dereferences and grabs a member thing. We can treat or think of these iterators as if they were pointers. At least the syntax is the same as if it were a pointer. And so here I can do the same thing. I can grab, well, let me go ahead. Oh, so this is just printing stuff out. So we should see first print out twice here. And so we should see I love C++ printed to the console twice. Here I'm actually changing what this is, the third member variable for IT. So let me go ahead. I didn't create IT. So here's IT. There's this. And so let me just steal this arrow. And so IT refers to the first robot within the list. Let me get rid of this R actually, because it actually isn't that. But again, more on that in a moment. And so here I just read first twice. Here I'm actually changing this to 2.718. So it's a different number altogether, 718. And then, well, there's a big question mark as to what this is doing, but we'll talk about that later. So let me just get rid of this, and we'll expand upon what is actually going on in a second. We'll examine it. Let me get rid of some borders. Let me just go ahead and complete this. Okay, and so here, what am I doing here? I am seeing out not IT, but third of R. And so let me go ahead and execute some of this. Let me get rid of this. And so the question is, there's two possibilities, right? There's one possibility is that this would print out, well, this. There's another possibility that it will print out this, right? Those are the two choices. Let's see what actually happens when we print this out. Let me go ahead. Actually, did I set this to start up? Yep. So let me evaluate this. And so here we see, well, the pushing our robots, that line, the I love C++, I love C++, the changing of the number, and then going back to robot R and asking for its third member variable. We see that it prints out 3.14159 and not the 2.718. And so what is the implication here? It seems like this, when we pushed R into our list, it seems like it made a copy, a new copy of R. And so this, whatever this is in a completely different memory location than the original R itself. And so that's kind of weird, maybe. But let's talk about the other implications with regards to this particular behavior that we're seeing here. And so since these are in different memory locations, what happened with this fourth memory variable for R? Right? And so it seems like it copied everything over into this particular the memory from this memory location to this memory location and so on. And so we should expect, if that behavior was the same for all member variables, whatever was in this member variable should also be copied into this member variable. And so it seems like the picture is actually like this, right? And if you recall, this is the telltale signs of a shallow copy, right? And so, and again, shallow copies are typically bad in situations in which you have pointer member variables who point to dynamically allocated memory, in particular who own this memory in a sense. And so right now we have two robot objects. Yes, they resemble each other, but they point to the same memory location. And so this will lead to a lot of issues down the line. And so let's illustrate this, right? And so here, let me bring this line back in which I print out what's currently in R, right? And so I go to my robot R, I get the fourth pointer, the member variable, which is a pointer, I dereference it. And so we should see 42, and I'm gonna go to my iterator, which points to this robot, and I'm going to dereference it and change it to 10. And so this should print out 42. And if what we discuss is correct in terms of the shallow copy behavior, we should see that when I have R again print out what's fourth is pointing to, or the value stored within the memory location at the address fourth, we should see this print out 10. All right. And so essentially what I'm saying is that Here we print out 42. Here we actually go back to this memory location, change this to 10, and then what we print out here should be 10. And so let's go ahead and evaluate this. And so the first few lines are, whether they are, yep. So we see that this printed out 42. We changed this through IT, not R, and that also changed R's fourth, or the thing that R's fourth is pointing to 10. And this is bad, right? And so the implication here is that if you're going to have, well, the question is, so what is being done here? Remember, there's two possibilities. So we tried to make a copy of the object by pushing it into our list. And so there's two functions that did this. One was the copy constructor, and the second was the assignment operator overload. And to determine which is which, I'm going to go ahead and add some code to our robot class. All right, and so then if I go up here and add this, which is a copy constructor, and after we execute this line of code, if this was invoking the copy constructor, then we should see this print out to the console. And so let me go ahead and just get rid of some of this other code that we don't need. Let me go ahead and evaluate. It doesn't like. Oh, so yeah. Now remember, once I start defining constructors, I need to define all of them. This wants to invoke the default constructors. So let me go ahead and bring that in as well. Okay, there it is. There's a default constructor, there's a copy constructor. And so now everything should be okay. And so after we see this, we should see this. Well, if it is invoking the copy constructor, we should see this. So let me evaluate this. Okay, and so this first robot R calls the default constructor, which should be clear. And now pushing robot R into robots, calling the copy constructor. And so when I'm pushing robots into my list in this way, I'm actually creating a new robot who is a copy of an existing robot, in this case R. And so seeing as how this particular implementation for a robot has a pointer which points to dynamically allocated memory, I ought to fill this up with, well, the code that we expect in terms of making sure that this particular robot points to its own version of whatever this is. Okay, well, that's just tying in some of the things we talked about. But just remember, when you're pushing things into your container classes or this STL container classes, it will invoke the copy constructor. And so that's something to keep in mind. Okay, and so that's how you can interact with STL using your custom objects itself. And so moving on from this, let's talk about other containers that are useful. In particular, one that is extremely useful, let me go ahead and slide this down, is this thing called a map. So let me set this up. And so a map is considered what we call an associative data type. And in particular, it associates two things. In particular, if you think about a dictionary, we are associating a word with its definition. If you think about a menu, you're associating, say, an item with its price. And there's many, many, many such relationships that follow this paradigm, and which makes maps, or this idea of a map, or even in some languages they use the term dictionary, extremely useful for the programs that you write. And we'll see this occur again and again. And so let's go ahead and talk about how we use the STL map. So it's in the map library. I'm using the map. And so I can declare a map in this way. So this is a bit different, right? And so there's two templated parameters here. And so the first one is indicating the first thing. And so if this were a dictionary, this would be the word, and then the thing that is associated with it. Again, if this were a dictionary, this would be the word's definition. In this example, what I'm doing is I'm relating or associating a person's name with their phone number. And so the way I would populate this map is to say, well, I call the map itself, and I use the indexing operator. And for Jenny, I am going to associate her phone number in this way. And so what does this look like? Let me go ahead and create some things here. Let me just go ahead and make this into text. Okay, so first let's declare an empty map. So here is actually, here is my empty map. I probably could use I've just done this a bit more efficiently. But so there's my empty map. Its name is name to phone. And so I throw Jenny into my map. So here's Jenny. Boom. Okay, and the number, for some reason, it's just Excel and numbers. So this is a text. So there's her number. Let me throw long into the map. So let me do it this way. There's long. That's his number. And then let me go ahead and throw Alan into the map. Well, it doesn't matter. There's no. Well, I kind of want that space. Never throw it up here. Okay. Slide these people down. 2. Throw Alan into the map. Okay, and so one thing you may have noticed is that I threw them in a particular way, in particular in alphabetical order. That's something you're gonna have to memorize with regards to these maps. There's a few. So there's 2 things. Maps, STL maps. So the items within the map are ordered. All right, so that's one key thing you have to remember. And so when I place something within the map in this way, it will order them based on the keys. All right, so ordered on keys. So yeah, so these are on the first item. So these things we call the keys. This is the value associated with the key. And then the other thing is that what we'll see in a second. Well, I'll illustrate it and then I'll place it down here as a key point. So anyways, so again, so I place them in. It's ordered. And so if I want to iterate through this, I could create an iterator for a map that associates strings with integer in this way. And so declaring this will create a iterator it. Let me go ahead and slide this over a bit. Boom. And so right now it doesn't point to anything, but it seems like what I'm doing here is I'm going to my name to phone map. I'm looking for long, and I want this to point to that particular item within this map itself. And so what does that look like? So after executing this, we should see this point to long, like that. And then after I have that, I can go ahead and print out this thing called whatever the iterator is pointing to, which is first, and then the key, and then the value itself second. So I should see, well, it changed this, but this should provide to me my name, long, or the name of this particular entry within the map, and then the value that's associated with it, so long's number. And so let's go ahead and evaluate this. Boom. Yep. And so for some reason it's, I think it's because integers are not large enough to represent this. And so let me change this. I need more precision or more bytes. Let me go ahead and do this again. Okay, so since I changed this to be associate strings with longs, I need to change this. This might not even be big enough, but so yeah, so it's not big enough. I need more. Let's see, more numbers. Unsigned would probably do it. So that'll give me twice the range. Unsigned long. There we go. So now, anyways, so now this is kind of strange, right? And so it seems like each of the entries within this map, it seems like it packs things into what you can imagine as being a struct, right? And so you can think of each element per, in a sense, think of it as an element is dressed up like a structure, right? So there's a first thing of certain type. In this case, string is the first thing, and then the second type is going to be the, well, in this case, unsigned long, and then a second, right? And so you can imagine in each of these entries within the map itself looking like this. It's a bit more complicated than that, but I think you get the general idea. And so that's what the map looks like. Let me get rid of this because it isn't quite accurate, but it's just so you can develop a mental model for what this is like. And so that's how you can refer to items within the map itself. And of course, I could use this iterator to iterate with using a loop, using the same bit of code that we see on the screen so far. Okay, and so given all this, now that we have all of this, let's examine what happens if I try to do this. So let me go ahead and copy this, and let me change this to say 5. And so what do you expect to occur here, right? So already we have long in the map. And so doing this is, well, there's two possibilities, right? It might be that we create another long, and that long, if I had more space here, this would get 5, and so I have 2 longs within this. And let's see what happens. Let me go ahead and iterate through this. So let me use the same iterator. Let me actually get rid of this, and I'll iterate through for this iterator, beginning at the beginning of my map name to phone. Again, actually, while IT is not the end of my map, IT++. So let me go ahead and see out. Well, I probably will need, well, I can do it one line. So see out the thing that IT, I need to, IT dot first, which will be the name of the person, space followed by their number. So see out IT dot second, and so this will be their number, and then end line for formatting. And so this will print out, iterate through. We should see Alan, his number, Jenny, her number, long, and then the original number for long in the order that we see it, because again, maps are ordered on keys, so it should be in alphabetical order when we iterate through it. And so after I change long's number to 5, let's see what we get. So let me go ahead and evaluate this. Okay, yeah, so the first iteration goes through what we expect, right? And so in alphabetical order, Alan, Jenny, long, and their numbers. And so the second iteration, it seems like I didn't add a second long here with a different number. It seems like I went to the long that already exists and changed his number to 5. And so this is another property of the maps within STL. All of the items are unique. So all the keys are unique, right? So unique keys. And so anytime you modify or if you refer to a key that already exists within a map, it simply changes the value associated with that key. All right, and so again, this is just something you have to bear in mind. We'll get into the nitty-gritty details later on when we start talking about other data structures. Okay, so that's introduction to the map. That's how you can use an iterator to go through the map. It's a bit different because with the list and vectors, the iterator only had one thing to refer to, the one element. With maps, there's 2 things, right? And so that's why we have this first and second, to distinguish between the 2 things that a map contains, or an entry within a map. Okay, and so given all this, there's something that we need to be a bit careful with, because remember, this idea of ordered on keys, this worked fine with strings because, well, C++ knows how to order strings. What happens if we want to utilize custom objects with a map itself? What are the implications here? So let's go ahead and examine that particular case. Let me get rid of some of this code. Let's examine map of objects. And so here I have an object called student. A student has a name and an ID associated with them. And so what I'm going to do here is I'm going to associate a student with their GPA, right? And so the key for this map object will be on students. And so this is a custom object. And so what does it mean to have students placed in a certain order? Well, hang on, let me go ahead and go through this code and we'll examine this. All right, so first what I do is I create a student S. S's name is long, his ID is 1, 2, 3, 4, 5, 6. And so let's go ahead and, well, that's this idea of putting long within this particular map might look like this. And so let me go ahead and so what would this map look like? right? And so in this case, let me create some space for a map. Boom. And so we still have first and second, but in this case, first is a bit different, right? So let me make this a bit larger. In fact, I don't think this will be adequate. All right, so let me create, the first in this case is an actual object. It's a structure, right? And so let's make this into, well, it might be better just to create long by himself. So let me create some space here. Get rid of all this, I don't need it. Okay, so here's what a student looks like. Here's a student object. So in this case, this is student S. S has a string, and then, or a name that's a string, and also has an ID, which is an integer. And so here's what a student looks like. More space than I need, but that's okay. Okay, and so let me go ahead and grab this. And so within the map, let me just place this in here. There is a student, but then again, this is the first thing, right? So this is first. First refers to the key. Second is whatever it is. Let me, boom. Second is this. This is the first entry within the map. Okay, and so when I create long has, or create student S, that's his name, that's his ID, and I place this particular student into the map, which in this case makes a shallow copy because I don't have a copy constructor for student, but that's okay because I have no pointers pointing to dynamic allocated memory. And so I place essentially these values here associated with the GPA 1.2. And this is totally accurate. And second is spelled with an E. An E, not a 2. Okay, and so given this, if I want to place another student into this map, let's say, let me create another student. Let's call this G. And let's call this person Kevin Pavia. His IDs might be off by 1-7. The question is how do I, what order do I place? Again, so maps are ordered, and so how is order defined for students, right? And so what do I need to do here? Well, it turns out in order for this to even make sense, I need to tell the compiler what it means to order students, or so what does it mean to be S being less than G? And so you can do that by overloading the less than operator, right? So let me bring this up here. And so in this case, I'm defining my less than operator to say that if the name is less than the left-hand side of the operation, the left-hand operand is less than the right-hand operand, then left-hand goes before, right? And so I'm ordering this based on name, but you can use whatever logic makes sense to you. And we'll see some more examples later on. But again, so if you want to use this map and the key that you're associating with other things is an object, you're gonna have to tell the compiler what it means for these particular objects to be ordered, and that you can do that by overloading the less than operator. All right, so let me go ahead and evaluate this. It didn't complain, and so let me go ahead and enable the console. And some of these context menus doesn't show up in OBS, and so if you're not seeing some of this, that's why. But I'm messing around with the context. And so let me go ahead and stud to GPA. Oops. GPA, and put in G, and Kevin's pretty smart, and so he's 9,000.0 because it's a floating point. Okay, and so let me see. So in this case, Kevin, if I iterate through this, despite the fact of me putting long first, if I iterate through this, I should see Kevin printed out first. And let me go ahead and copy paste the code I had from this, in which I iterated through the map. Yeah, this is a better example. So let me go ahead and just copy this. I'll modify it to work on this. And so in this case, it's a map of students and integers, and so I need an iterator for that type. And then the name of my map is this, and then all this should be the same. And so, oh, so what does it mean to print out a student? Let me go ahead and just say name. I just want his name, and then the second thing is just a GPA, so it's just a number, so this makes sense. Okay, so let's go ahead and evaluate this. Yep, so we see that Kevin is, K is less than long within the ordering of these strings, and so Kevin occurs first within the iteration of a map. Okay, so that's that. Just some cautionary tales with regards to using maps. So another type of associative container, it's classified as an associative container. It's called a set. And so let's go to the set. Although I don't, oh, there it is, I lost it. And sets are, well, they're pretty basic data structures. And so let me go ahead and just create some code for it. So here's my main. Let me go ahead and declare a set. In this case, let's just keep it simple to say it's a set of integers. Let's call it A. All right, and so for sets, you insert stuff. All right, so let's say I insert 2. Let's say I insert 3, and so on. All right, so let me just copy paste this. 3, 4, let's do 2 again, and then we can, again, with all these containers, I can request the size. In this case, we should have this print out 4. Well, no, that's part of this exercise. What should this report? And so if you ever took if you have taken a data or a discrete math course, you should know that sets have unique items within them, just like a map, right? So maps are unique on keys. Sets are also unique on the things that you place within them. And so let me draw up my set. Let's suppose this is my set. Let me get rid of all this. Control X, Control V. And so let's say this is my set A. And so inserting a 2, essentially, you can think of it as a big bag of stuff, right? So I insert a 2 in there somewhere, I insert a 3 in there somewhere, I insert a 4 in there somewhere. And then when I go to insert 2, it actually just doesn't do anything because the 2 is already in there, right? So for sets, you have to remember that the things that you place in there are unique. And so that indicates that the size of this is not 4, but rather 3, despite having 4 inserts. All right, so let me go ahead and evaluate that to illustrate that point. Oops. That was the last project. Set as started. Boom. Okay. And so, and then I forgot to do the thing. Of course, I could do the little hack, but we try to do things proper here. So, okay, so enable the console. So boom. So yeah, so the size of the set is 3, not 4. Okay, but we'll talk about how a set's useful later on. I just want to introduce it to you here. But anyways, that's a set. Now, let's talk about how I can use this set for various things. And so there's one thing you actually have to, another thing that's similar to maps is that the items that you place inside the set are actually ordered. And we'll talk into detail as to why this is the case. This is part of the way a set is implemented. Well, the reason for this is the way a set is typically implemented. And again, we'll talk about the details as to why that's the case later on. But let me go ahead and change the order of all this. And if I iterate through this set, we should see it print out 2, 3, 4 because it's ordered on that, right? And so let me go ahead and create an iterator for sets. Actually, I'll just loop through. So I need a set integer iterator. Let's call it IT. Well, I want to have it begin at the beginning, as with most good stories. I want to go until my iterator is not at the end of my set. Ent plus plus. And so again, so there's only one item within the set, and so there's no key value going on here, so it's just dereference IT in this case to get the thing. And so let's go ahead and evaluate this. And again, it's ordered, so 2, 3, 4. Boom. 2, 3, 4. Yeah, so this 3 is the size, and then 2, 3, 4. Okay, if that's confusing, let me get rid of the printing of the size and try it again. Because that confused me for a second. I was like, hang on here. Something's not quite right. Okay, so there it is. So the iteration here just goes 2, 3, 4. And so again, if you want to place objects within your set, you have to tell the compiler what it means to order objects. And so this is just something you need to bear in mind if you want to use this container to store objects. But anyways, that's that. The same issue as with regards to the map itself, where you need to tell the compiler how to order the keys. And so a few more things, right? And so these are all great, but sometimes you need something a little bit more flexible, or not flexible, but the problem that you're trying to solve involves layers of things interacting with one another. And so suppose for a moment that I wanted to keep track of, I wanted a container or something to contain students again. So I want a bunch of students, but for each student, I want to have a list of all their courses, right? Or something to keep track of all the courses each student has within them, right? And so what does this look like, for example? So if I have long, so here's long. Let me go ahead and let's suppose long took the class, well, CS 20A. Let's say long also took the class Art History 1. Let's say long took the class Math 8. All right, so he has 3 classes, Math 8, and I know it's kind of the formatting is kind of off here, but I'm gonna delete this in a second. But just so you understand the problem we're trying to solve, there's long, but then let's go ahead and say who else? Let's have another student. Let's say Mary, and just for simplicity's sake, let's just say Mary took the same classes. Although I'm sure you can you understand that these can be different stuff, right? And then let's say Tom. No, Amanda. Like this, and then let's say Neil. And then again, these can all be different classes. It's just I just want to quickly illustrate the problem we're trying to solve here. And so, how would you implement this using STL? And so, well, first of all, it seems like, yeah, so this I can represent as strings, right? Because they're just names for students. And then, so this, I can, well, this seems like it's a bunch of classes, and so I have a few choices of how to represent these classes. In particular, I could use a list, right? A list of classes for long, a list of classes for Mary, a list of classes for Amanda. In particular, a list of classes that's associated with Amanda, a list of classes that's associated with Neil, and so on. So this idea of associating 2 things, despite this sort of being more complicated than just a single thing, should indicate to me that I want to use a map-like object to associate a name with a list of classes. Now, it's a bit more complicated than that, right? Because I can't just say, so yeah, so the first thing here is, say, a string of names, say, but what should the second thing be, right? And so I could have another class to represent this, but when I say the word list, that should kind of give away how I might, or a choice in which I can use, or a design decision I could use to implement that sort of idea of a list, right? I could use a list. I could say the list of, well, and then what is this? How do I represent this? And so let's make it a little more complicated. Let's suppose we have something called a course. We have an object called a course, and within the course itself, I have something called, the department, and then the number associated, or the number associated with the class itself. And so what does this look like? Let me get rid of this and go to the actual project. This guy here, let me go ahead and set this as startup. Okay, and so let me go ahead and put some code down. Let's create this class. or this course, or this class is called a course. So within a course, I'm gonna have, I don't know, well, let me make everything public just to make our lives easy. Let's say, so a string for department, and then an integer, well no, another string because of the A for 20A, string for number. And so now we have this, and within my main, I can, well, let's go ahead and create a map that takes names of students, strings, and associate with that their list of courses. Boom. And then let's call this CRS map. And then here I don't quite have list just yet, so let's include the list library since I'm using it. And so that should fix this. And so now it's an empty map, and so I can go ahead and, well, let's create a bunch of courses, right? So let's create a course C1, course 1. I don't have a default constructor. Let's make one to make our lives easy. So course, Coruscant. Let's have it take 2 strings. So D, or the department, and then the name of the number, sorry. In which case I will associate that, and then with num, this gets n, and then boom, that's that. Okay, and so with all of this, I can go ahead and create a course for CS 20A, and then I can create another course, C2, call this Art History 1. Let's create another course, C3. Let's call this Math 8. I get kind of confused with the auto completion sometimes. Okay, and so that's that. And then so I can go ahead and populate this map by saying, okay, so CRS map. I can place within this for, say, long. I can have his list of courses. Well, this is a list, right? So I want to push back, if you recall, into this a course. So C1, I can do this for all his courses. All right, so C2, C3. And what does this look like? And so, I mean, one way to imagine this is like, so here's my map I created. So the first thing is the string long. The second thing is, well, this list of courses, right? And so after these 3 pushbacks, we should see these 3 items within a list. Again, if you go back to when we introduce lists, this is what you can imagine. Okay, and so actually this picture isn't quite accurate. Let me actually like this. It's weird. I don't like. Again, we'll get into the details as to why I'm having it look like this. But anyways, so that's that. Get out of here. Okay, so that's a picture, and I can add more students with their list of courses. And so you could compound these containers in this way to create or to implement more robust behavior, or have all this flexibility by compounding all these different container classes to implement certain particular solutions to whatever you're trying to solve. Okay, and so I think that's all I want to talk about with regards to the container classes within STL. And this is just an introduction. There are many containers, and so as you're maturing as a C++ developer, you're gonna spend plenty of time looking up the reference sheets for all the different containers that you can possibly use. But I just want to spend 1 second to talk about the other end of the other spectrum of data structures, which is the algorithms, right? Data structures are not independent things. You have to think about both data structures and algorithms in conjunction with one another in order to have a complete solution to your problem. And so incorporated within STL is algorithms, right? And so one such algorithm, again, there is many algorithms, is the sorting algorithm. And so one way to use the sorting algorithm is, well, first, these algorithms are within the algorithm library, right? And so from this library, I'm using the sorting algorithm from there. Although there's other places in which you can grab the sort algorithm. Some classes have the sort implemented within themselves, but anyway, that's besides the point. But anyways, so from the algorithm library, let's talk about how you can use the sort function. And so here I declare a vector of strings. Its name is n. With an n, I push back a bunch of people. And so Carrie, Bart, Alex. And so to sort this, I can use this bit of code. I pass in essentially the beginning, an iterator to the beginning of the container, in this case this vector. And then in this case, I indicate where I want it to sort up to. Right, and so this will just, I mean, there's only two things here, but I can tell it to only sort up to a certain amount of elements, right? So if this had 1,000 elements and I wanted to only sort up to maybe 900, this would sort up to 900 elements, right? Or I can have it sort to the end, which would simply be done like this, right? And so you're passing into it the beginning and one past the last element within the container class itself. It turns out that this function is also overloaded for arrays, right? And so I can pass in the address of the first element within the array and the last element of the array. And of course, you should know by now that I can also use this syntax, right? So ARR plus 4, right? So up into the elements I want to sort. Pretty straightforward. And you can do this for all container classes. One minor thing though, again, when we're talking about sorting objects, so if we go, say, to this example, so here I have a dog class. I have a parameterized constructor which initializes its name, bark, and bite. And so a dog has a name, it has a particular bark volume, a particular bite pain that it can give to mailman. And so it has a couple getters, and then I overload the assignment or not the assignment, but the lesson operator. And so in order for me to sort, well, actually, let me go ahead and go to the main. I also have a print function that iterates through a vector of dogs and then prints their name. Right. So this is just a utility function. And so here I create 4 dogs: Fido, Butch, Moon, and Skip. And so this is their, I believe, their bite volume, their bite, and this is their bark, right? And so it seems like Moon has the biggest bite, and then Skip. So Skip and Fido have the same bite. Butch has the weakest bite, but between that, it seems like their bark volume, Moon and Skip have the same bark. Butch has a pretty weak bark, and Fido has the weakest bark. Anyways, that's what it is. I create a vector of dogs, I call it kennel, and I put all the dogs within my kennel by pushing to the back of the kennel itself. And so I can iterate through, in fact, I don't need this because I have my print dogs list. And so from here, I can go ahead and print the kennel. And then I can sort the kennel, and so I just provide the beginning of the kennel and then the end, which is one past the last element. And after the sorting, if it will invoke this particular operator overload for less than, right? And so it will just sort them by names. And so after I sort them, it should print out alphabetical order, right? So Butch, Fido, Moon, then Skip. This first print dog should just print it in the order that we see here in terms of the push back, right? And so the first element, well, it starts out empty. We should see Fido. So the first printing should print Fido, then Butch, then Moon, and then Skip. And then after that, this print should print Butch, Fido, Moon, and then Skip. Okay, so let's go ahead and execute this. Let me set this as startup. And I wonder if okay, so the console's enabled. Okay, so let's evaluate this. Okay, well, there's no, I didn't put an end line, put the end line at the end. Okay, so yeah, we see Fido, Butch, Moon, Moon, Skip, and then we see Butch, Fido, Moon, Moon, Skip. And so this sort will make an attempt to sort it based on whatever operator is being overloaded for less than for this object itself. Now, there may be situations, and in fact, there will be situations as you go through your C++ programming career in which maybe I don't want to use this sort. This might have some application for certain situations, but every now and then you might run into a situation in which, well, I don't want to sort them based on their names. Let's suppose I want to sort them based on their byte, and then if their byte's the same, I sort them on their bark. But I don't want to get rid of this, right? I want to keep this because this might be the default behavior in terms of sorting or in terms of what this means with regards to dogs. But for various situations, you might want to have this sort use a specific or a special type of comparison algorithm to sort your dogs. And so the way to do that is, well, first of all, let's go ahead and define that. Here's my custom compare function for dogs. Let me just grab it and move it up here. So it's returns a boolean because that should make sense. I'm returning whether or not a dog's greater than another in some sense. And the way this custom compare works is that I'm first comparing them on their byte. So a dog with the largest byte is considered first or before other dogs. Otherwise, if they have the same byte value, I go ahead and use the bark as a secondary comparison. And so I can have my sort function sort them instead using this custom compare, and then there's a bunch of different ways of doing this. You can just pass in the function name. It might be a bit weird for many of you, but you know, so this will work. There's other ways of doing this. You might hear the term function pointer, you might hear the term functor, you might hear the term lambda function. All are different ways of doing the same thing in terms of having this sort function operate in a different way. In particular, I have a custom comparison with which I can sort my dogs within this kennel. And so given this, let me go ahead and print my kennel, and let's first talk about what we should expect to see. And so again, so we first sort on bytes, and then if the bytes are the same, we sort on barks. And so it seems like Moon Moon has the largest byte, and no one has the same byte here, and so we should see Moon Moon. And so there's no new line, so I'll just leave a space. And then the person, well, there's two dogs here with the same byte value. Skip and Fido have byte values of 10, but Skip has a larger bark. And so Skip should occur before Fido, and then Fido, and then Butch is last of all. And so let's go ahead and evaluate this. And so we do indeed see Moon Moon, Skip, Fido, and Butch. And so this is how you would pass into the sort function a specialized comparison that might be specific to whatever you're doing at any particular point in time, while still maintaining the original operator that might be, you know, something that you want to keep around with your object. But anyways, this is just a short introduction. Again, there are many such functions. So we will talk about the details of how all of this works, what we talked about so far throughout the remainder of this course. But hopefully this proved useful. If you have any questions, feel free to ask. And I hope you have a good remainder break. What? What is it?